Today's webinar is on RSData. I'm Alireza. I've been with Rocscience for more than a decade now as a geomechanical specialist, and today I have the privilege of hosting this webinar with Dr. Reginald Hammah. Reginald has been with Rocscience ever since that, even before Rocscience became a company. So Rocscience, we are a world leader in developing 2D and 3D software for civil, mining, and geotechnical engineering application. You can categorize our tools into 3 major categories. You can use our tools for slope stability, excavation design, and geotechnical tools. RSData today is one of the geotechnical tools that we will be introducing again. Like slide 2 is our 2D limited review slope stability analysis tool, which is top of the line in the market, and you can do lots of functionality with it. It has lots of features and packed with lots of functionalities in there. In slide 2, when you're defining any of these models that you have, you are going to define materials, geomaterials that you have in there. And the materials are represented in a simulation by their strength type, which is shear strength of the material. We have an extensive library of shear strength equations and functions, like general Brown here, more Coulomb, and you name it, we have it in here. So these are defined using these equations and bunch of numbers to assign values to that, and we define that shear strength for the material. We have the same thing in slide 3 as well, the same library. S-wedge, another tool that we have for rock stabilities, is used for surface wedge analysis. Again, lots of functionalities in there. When you are defining your model, you have these 2 joints that are forming the wedge. And joint 1, for example, here is using the shear strength model of Barton-Mendes with this equation. Joint 2 is using more Coulomb criteria with this equation. Again, you have a bunch of numbers here to define that material behavior. So these numbers are coming handy. We have the same thing for unwedge, rock plane, and rock topology. You have to define all these properties for them. More complex tools that we have RS2. This is our 2D geotechnical finite element analysis. Again, it's packed with all those features that a geotechnical engineering and mining engineer would require to do their simulations. Same thing in RS3, our 3D software. And in these, again, you are defining those materials, those geomaterials that you have in the model. It's more complex than the shear strength only. You are defining constitutive equation, like for example, one of the fancy one or the complex one, north and here. You are defining that constitutive equation with all these bunch of numbers that you are putting in. Again, like I mentioned, we have an extensive library here. You can see it here. We have categories of constitutive equation. You can define them, you can use them, but any of them that you go to, you will have to define all these material properties and assign numbers to them. Now, I'm giving you this quote from Everett Hook. He says, assigning numbers to geology requires a delicate balance between the commonly held opinion that geology cannot be quantified and the overly optimistic view that every physical quantity can be described in precise mathematical terms. So that's where we have RSData. RSData comes in to be a versatile toolkit for the analysis of rock and soil strength data and the determination of strength envelopes and also other physical parameters. The main functionalities that we have envisioned for it is to analyze and investigate material strengths and behavior, compare the strength criteria and constitutive behavior with the actual data from laboratory or field, choose the appropriate strength criteria and constitutive model, and then calibrate the strength criteria and determine and identify some of the constitutive models. The feature will be added later on as RSData is going to grow, but we have a bunch of these features already implemented in it, and we are going to introduce them to you guys. So with that, I'll pass the presentation to my colleague, Reginald, and we'll follow from there.
Thank you very much, Alireza. Good morning, good afternoon, good evening, everyone, depending on where you are and what time zone. Now, thank you very much for joining us. It's a privilege for us to be able to share these thoughts with you. I'll be focusing on the rock aspects of RSData, how to analyze rock strength in RSData. I'm going to show you how things in terms of functionality are similar to rock data, but with time we will add more. Alireza already explained some of the fancy constitutive models that we have to deal with, particularly on the soil side. But I believe on the rock side, things will also be getting more and more sophisticated as we go along. So the program has been developed to accommodate all of that as the few new features become available.
Underlying every numerical modeling exercise in rock mechanics is the need for good quality laboratory data, because the strength of rocks is characterized starting from intact rock. We perform triaxial testing on intact samples, record the data, and then we curve fit to it. The curve we generally use in rock engineering is the Hooke-Brown criterion, which was developed to model shear failure of intact rock. So in today's webinar, we're going to look at fitting the Hooke-Brown curve to 3 different sets of laboratory triaxial test data. So that is what we are going to be doing in the webinar today. So I will select, when you start rock data, you have an option to select which template you'll be using. Let's select the rock template and then select OK. When that gets going, we see that there is a visibility pane which has several objects listed. The root object is the rock template, and beneath it we have other properties, and these are displayed as nodes. Now, just below that we have a properties pane. So if you select an object in the tree, a node in the tree, you'll see properties peculiar to that node listed in the properties pane, and you can change them or play around with them. So having started that, like I said, I'll be fitting 3 data sets in this example. We'll store all these data sets under one RSData project file. That is what we will be doing. RSData was developed to help us maximize the information we get from triaxial test data. Rock data allowed us to fit strength curves to data. RSData is going to be fitting more than strength curves. But for rock now, we will be fitting strength curves. However, we can also simulate these curves. So that's what we will be doing. I'll select the name of the template and change it, give it a material name. So the first material I'll be fitting to is called Stone Mountain Granite, and the data is from rock data. The old rock data had this data set. So I'm going to capture data from that, and I select. So I've done that, and now where we input the lab data is under what we call failure states. So if you go under failure states, there is a state 1, it's a default state. Now that lists sigma 3 and sigma 1 values for a triaxial test. So we are going to be pasting the Stone Mountain data into this section of RSData. So let me select the Stone Mountain data and copy it. And then I'll go back to RSData and paste into the spreadsheet. So I have input my triaxial data for the Stone Mountain Granite. Now we can see that it is yet to fit the curve to the data. The curve is in one place, the data is elsewhere. So to undertake the curve fitting, we use what we call calibration. So I'll right click on the template name, the original name, choose apply calibration, select the calibration node, and specify the calibration parameters, which includes specifying the algorithm I'll be using for the curve fitting and the error summation type, and then the error type itself. So I'll choose the modified cuckoo curve fitting method. I'll choose error summation to be basic and the error type to be absolute. So we can now see that RSData has fit a curve to the stone granite triaxial data we imported. The next thing I'm going to do is I'm going to simulate this data. So to do that, I right click on the template name and choose apply test simulations. And I'll simply choose test 1. So the material name is Stone Mountain Granite. I'll just choose test 1 and select OK. So my simulation has been added as a node. Now I want to perform a triaxial test. So I'll change the type of test to triaxial test, and I will leave the initial confining stress as the default 0.1. Let me put a maximum strain value of 5%, so 0.05. Okay, so we've done that, and then let's select. So once we do that, we can see the path, this simulation on the stress path tab. So by default, we are looking at the strength graphs. Now let's go to stress path graphs. And so I see the stress path for this test simulation. When we fix that Hook-Brown curve to the data, we've got a strength of about 75 or almost 80 megapascals. We can see that if I select the material name, and it tells us 75.3 megapascal. So that's the peak strength we see, and the post-peak is set to be the same, set residual to post-peak. So that is what we can see. And when I select the test again, we can animate this test. So I make sure that the animation is set to this particular test, which it is the only test we've created. And I click animate, and that animates the test. Now I'm going to add the data for the dolerite. So I will go to add materials and choose rock template again. And I will change the name. So let me go to my properties, and I will change the name to dolerite. Okay. And then I'm going to add the test data, the laboratory test data for the dolerite. Once more, I'll go to my Excel spreadsheet, select all my dolerite data points, and then I will go back into my RSData, select the first row and paste my dolerite data. And let me go back to my, so I do that. Now let me add a calibration node for this material so I can calibrate a Hook-Brown strength curve to the data I just imported. I'll go to the strength graph so you can see the new data is the blue point. So once again, I will select apply calibration, select the calibration node, use the same curve fitting parameters we used before, and I have fit a Hook-Brown curve to that set of triaxial data. So that was for the dolerite. I am going to repeat the same thing for the last set of data, which is high quality testing in the tensile zone of Carrara marble. This was done by Ramsey and Chester. So let us fit the Hook-Brown envelope to that data. So as we did previously, we'll select the rock template. I can change the name of the template to Carrara marble just to make it easier for me to know what which test data is where. So Carrara marble. And then, sorry, just a second. And then I am going to add the failure states, the laboratory test data for the Carrara marble. So once more, I'll go to my spreadsheet, choose my Carrara marble data, and then I'll copy it, go to my RSData, select the first row, and paste the data. So now I have my Carrara marble data listed, the green data points. I'm going to add a calibration node. So I'll apply calibration, and then I'll select the calibration node, choose my same curve fitting parameters again, absolute for this, and I have the Carrara marble also fitted to the data. Now I can animate that as well. So if I want to animate that, let me select apply test simulation. I'll use the same parameters I set for test 1, select OK, and then I can select that test, go to the stress path graphs, and then I will choose animation, and I'll make sure that will be Rock 2. I see the name here is listed as Rock 2, so I'll do Rock 2 test simulation and select And that's the simulation for the Carrara marble based on the stress path we specified. Now that we have done that, I'm just going to add a generic material. This time, I'm not going to kerf it. I just want to see if I perform a post-peak analysis, whether my simulation is going to correctly show me that post-peak, that drop in strength after peak is attained. I'll specify a lower residual. So let me do that. I'll add a new material, add rock template. That's a new material. I'm not going to name it because it's going to be just generic. I'll select the name from the tree, and let me try with the MB, S, and A set of parameters. Now, let me try, and let's say I use an MB of, I don't know, 20, I'm just testing, an S of 1, so that's reflecting intact data. After specifying the new rock material, we are going to indicate a residual value that is much lower than the peak. So I'm going to do that in this dialog used in the properties pane. So what I'm going to do is, let me change this to MBSNA for an example, and let me change the MB value to 20. Let's change the S to 1 for intact rock, and the A is 0.5. Now I will uncheck the set peak to residual box, and then I'll specify a lower residual. So let me put an MB of 5, an A of 0.001, and let's try an A of 0.56. And then once I have done this, I will create a test simulation. I'll apply the same test 1, and we'll see what it looks like on the stress path graphs. So I will right click on this template, choose apply test simulations, choose test 1, select OK, and test 1 is applied. Now maybe I can play around with some of the test 1 parameters. I will change the lateral stress from 0.1 to say 10, and let us just try that. And now we will animate this chart once it's ready to go. So again, I've changed the lateral stress to 10. I've left the initial effective K, so the stress ratio is still 1. And the maximum strain, I have retained 0.05. And now we are going to animate this graph. So the way I'm going to do is I'll go to animation, choose that test, it's the last one, and I'll select play. And it shows the drop in strength once we hit peak. This brings me to the end of my the portion of the webinar on fitting curves to rock strength data when we are looking at intact rock testing triaxial. I will hand over to Alireza, who will continue and take us through the soil template part. Thank you very much.
So I'll start a new instance of RSData. I have it here. I'm going to click on it. It's going to come up, and I'll take you through the soil template that we have for RSData. So coming up, you're presented with this template. I'm going to go to the soil template. Click on it. Double click. It's going to start a soil template for me. And what I have here, I have the material at the top. It has a material model, which is here a Morculo material. It is plastic with the cohesion, friction angle, and all that, and you have the dilation angle 0. There's one test simulation on it. The test simulation is a triaxial test, strained compression under confinement of 100, and the maximum strain that I have on it is 10%. And the loading shear applied to this sample in 100 steps. So this is the behavior that you can see for this material. It's a linear elastoperfect plastic. So with in axial stress versus axial stress, you see that linearly increasing axial stress with increasing axial strain, and at the failure is going to go flat. So the level of stress is going to be flat. So for volumetric strain versus axial strain, you have the initial compaction in the elastic phase. When it comes to failure, because the dilation angle was 0, it will continue with plastic deformation at constant volume. If I animate this one, you can see how this stress path is actually forming. Okay, now within just this simple template, you can manipulate and change many of these properties to see what is the effect of each of these properties on the behavior of the material. Like for example, this dilation angle that I received many questions about it. So at the moment it is 0 and the behavior is elastic compaction, then you have the constant volume for failure. If I change it to 5, for example, you can see immediately within that volumetric behavior versus axial strain, it is giving you the compaction, and after that, at failure, you have the dilation behavior. Let me animate this one again so that you can see where the dilation behavior is starting. At the failure, you have the switch to dilative behavior. Now, I have 2 examples here for you. I have one example for a critical state model using modified CAM clay, and another one for sandy material. I'm using Norsand. So for the CAM clay one, this spreadsheet that is included in our RSData package, and also we're shipping it with RS2 and RS3, is one of the verification that we have for modified CAM clay model. This presents the analytical solution for a triaxial test under confinement of 200 with these material properties. What I'm going to do now, I'm going to compare this analytical solution to the solution that you can get numerically using that RSData. So I'm just going to generate this one in RSData, and then we can compare it. Just going to remove this and put it in my other screen so that I can read the material properties from this one. So what I have, before I continue, if you have any questions, please type in the question box, and we can address as many as we have time for at the end of the presentation. So for material models, what I had initially is more Coulomb. I can change this one to modified CAM clay, and all the properties for the modified CAM clay material model is appearing here for me. So the M critical state line, the slope of critical state line for this material is 1.2, N is 1.788. I have over consolidation ratio, this is 1, and lambda is 0.66, kappa is 0.077, and for the stiffness of the material, I have constant shear mode, constant Poisson's ratio. So this is the behavior that I see for this material in that triaxial test. Okay, let's go back here. Let me adjust this one, 0.077, and so for the test for this one, let me go to material properties one more time. So critical slope line is 1.22, N is 1.788, kappa is 0.007, over consolidation ratio 1, and lambda is 0.066. Stiffness is Poisson's ratio 0.3. Okay, so this is the behavior that we see for this material. Let me rename these. This one is going to be my normally consolidated clay, so NC clay for me. And the material model, I'm going to name this one NC for normally consolidated. And for test one, this is my triaxial test. The one that I have in that spreadsheet is under confinement of 200, so I will prepare the same thing here. So this is triaxial test, drained, compression, initial effective confinement is 200, and the strain range for that one is actually 20%, so this is 0.02. I'm just going to add a couple of more steps here so that it's going to be more accurate in prediction of the behavior. And this is the predicted behavior. Somebody asked actually about the cyclic loading for triaxial. If you have cyclic loading, you can add cyclic loading to any of the tests that they have defined in the RSData tool menu. So the next step, I would like to compare this predicted behavior with the analytical solution. To do that, I have one of these stress passes present for me here in this example. This would be a triaxial test, and it is drained axial loading starting from 200 kPa, and with the K naught of 1, I will import one of those CVS files that is actually presenting the same behavior that I saw in that Excel file. I have it presented here. Let me open the file. So this is axial strain, axial stress, and the volumetric strain. These are 3 columns that I will be importing here. You can copy paste, you can import. So I'm going to use the import function here. I can do import and point to that file that I just mentioned. So this is that normally considered clay behavior. I'm selecting this one. If the file is open, I get that error. Let me close this file. So this stress path, the red one, is actually added to the system, and you can see how close is the prediction that we have to an analytical solution. Now, I would like to see what is the behavior of my material if it was over-consolidated by a factor of OCR2, for example. To compare that one to this one, I can go add another soil template, and a second one will appear for me. This one is for now a more Coulomb material. Test number 2 is running on it. It is compression under 100 kPa. So what I have actually in my analytical solution is that one, so I will keep it the same. But the strain range is 0.2. And what I need to do, I would need to make this material that I have here to be the same as material at the top with OCR of 2. To do that, I'm going to go in my define material dialog here from the top. This is my normally consolidated clay. This is going to be my over consolidated clay, that OC clay that I have. And I will grab the first one and I say copy this to my OC, over consolidated clay, and say OK. In the OC, I'll change that over consolidation ratio to 2 and I'll press OK. So this, let me make it darker green so that we can see it better. So this dark green stress path you see here is the behavior of over-consolidated clay under confinement of 100 kPa triaxial test, and you see the elastic portion at the top, and after that you see that hardening behavior that is pushing the cap to give you that hardening behavior here. Let me rename this one to be my OC clay, over consolidated clay. And just to show you what kind of simulation we are seeing here, let me go to OC clay and test number 2. I'm showing you the animation for the stress path, and also you can see the evolution of the hardening and expansion of the yield surface. So the green material, the OC clay, has OCR of 2. So initial confinement is at 100. The intersection of the cap and the p-axis is going to be at 200. So this is the initial cap that you have, the elliptical cap you have for that critical state camp clay model. Now I'm animating it. Initially it's going to go elastic. It's going to touch the yield surface and it's pushing it up, and you have that expansion and you have that hardening behavior here. Now the next step, this one was over consolidated, but I want to see if I can see some of that softening behavior that we expect to see for highly over consolidated clay. To do that one, I will use the same material, but I make it highly over consolidated. I will add a material here. I'm not going to go with the template now. I don't have any stress path for it, for example, to compare. Let's go add a material. This material for me is going to be my highly over consolidated clay. And to this one, I would like to see the same test that I assigned to that over consolidated clay. So I would right click here and I say apply a test simulation, and test 2 was that triaxial test under confinement of 100. We'll add this one. And for the material, I will go to material properties dialog and create a new one. This one is going to be my highly over consolidated clay. I'll make this one actually bright red so that you can see what's happening here. I'll select one of the materials that I have at the top, copy the properties, all of it, to highly overconsolidated clay. Okay, and in this one, I'll make that overconsolidation ratio 5. So it's going to be highly overconsolidated clay. Okay, and I'll come back here. This entity that I have here, this material node that I have here, it has the test, but it doesn't have any material properties. What I want here is right-click, apply material model. I would like to add that highly overconsolidated clay material that I just defined. So I'll add it here, and this red line appears for me. So you can see clearly you have that hardening. It touches the yield surface, then you have the softening behavior coming back to the critical state. Let me turn off the very top one so that we can just compare these two. This one is my highly overconsolidated clay. If I go for animation, you can see that, okay, initially my confinement is at 100, and the intersection of cap and P axis is going to be at 500. So this is my initial OCR of 5. If I animate it, it is going to be go elastic, touching the yield surface, and you have the shrinkage of yield surface because of softening, and it's coming back to that critical state. Let me animate this one now. So it touched the yield surface, you have the softening behavior, it's coming back to the same critical state as you saw for the OC clay. So it is coming to the same level of stress in both cases. One of them was hardening because it was not highly overconsolidated. You had the initial stiffness, initial elastic portion of the behavior, then you had the hardening. The other one touches the yield surface initially in the dry side of it, so you have that softening behavior. The yield surface is shrinking, coming down to the critical state where your stress path, stress state is going to be at the apex of this ellipse shape at your critical state. Once again, if you have any question, please type in the question box. We'll try to address as many as I can at the end of the presentation. So that was the CAM clay model. Looked at normally consolidated, overconsolidated, and highly overconsolidated. We have an extensive library of material models in RS2 and RS3. They have not been populated in RSData yet, but they are coming in. They will be added. We will be having the same material model in all 3 products. And later on, when we have that, we can save all your material properties here, calibrate them, study them here, and save them and import all these material properties into RS2 and RS3 and carry out your simulations there. You can actually use this one as a storage for your material properties later on. Okay, close this one, and I will go for the other example that we have for stand is using Northern material model. The Excel file that I'm opening right now is the file that we received from Mike Jeffries. This one has his visual basic solution for the Northern material model, considered model, and in this particular file is calibrating the properties for Nerlach sand to capture the static liquefaction this sand has shown in an experimental lab experiment. So the red is the experimental data, the blue is the Northern simulation from the visual basic code that is behind this spreadsheet. What I'm going to do, I'll bring these two in RSData, and I'll compare these two to the simulation that we can get from Northern that we have in RSData. The same constitutive model is in RS2 and RS3 as well. So to start this one, I'll actually start from a file because I just wanted to have all these properties defined for my material. I'll start from this one. There's actually not much information in this one. The only thing that I have in it is that properties that I defined for that material model, that Northern. So if I show it to you, there's nothing here. This is my material properties that I have for that Northern model. So all the properties, the same as the one that we have in that Excel file. What I'm going to do, I'll add a material. This is going to be my Nerlach sand. And first, I will bring those data that we had from Mike Jeffries' spreadsheet file. To bring those, I can go to define a stress path. To define the stress path, these were all triaxial tests. They were undrained, loading direction was axial, and the initial confinement for the one that was the Visual Basic solution is 450. Let me just double check. These are the test simulation, 495 actually. So this is 495. And what we have, I'm just going to copy paste the data that I had there, bring it here. So this is all the data points that we have from the Visual Basic solution. I'll copy these, bring them to RSData. I click here at the corner, everything is selected. When I paste it, everything is going to come in. So this is like 4,000 data points here. So it's going to take like maybe a second or two. All the data points are coming in. And this is my my Jeffries Visual Basic solution stress path. I'll add it to the system. The other stress path that I have is, let me change the color to red. And this is the experiment. So the experiment is also a triaxial test. It is undrained. It is axially loaded. The start of it, the data is here. So this is the experiment, 498,979. I'm going to select all these data points. I'll bring them in. Copy this one, send this one down. All these values coming here. Initial effective stress is going to be 498.979. So these two are defined in the system for me in our RSData project that I have here. I say okay. Now I can right click here and apply it here with this one, or I can go here and say apply the stress passes that we have. This was the Visual Basic solution. This is the experiment. These are added to the Neuralink material that I have at the top. So I go to the stress path graph. This is the same thing that I showed you in that Excel file. Blue is the solution by Mike Jeffries, red is the experiment. Now, I would like to run the same simulation using the North-Sand model that we have in RSData. To do that, I will create that test to begin with. So the test is going to be defined here. This is going to be an undrained triaxial compression test. It will be triaxial test, undrained, compression, initial confinement is 495, and the range of strain that I see here is like 20%. So this is going to be 2.02, and number of steps, I'll add 400. Mike Jeffries was using 4,000, I'm using 400. These kind of material models that they use sort of explicit integration behind them, the number of steps might actually change the behavior a little bit, but not much. But I'm going to use a higher value than the regular 100. So this is defined. And I'll add it to the system. I can go from here or right click here and add it. I'll add it to Neuralink. And the only thing left is to apply that material properties, this one, assign that consistency model. So apply material model, give me the Neuralink defined with North-Sand consistency model, and apply it here. So the green line is what we actually predicted with using the North-Sand. Now, looking at the material properties, there are lots of them here. We can play with them and calibrate them as we please. But let me just animate this one to show you the static liquefaction process, and also we can look at how the yield surface of this constitutive equation is evolving. So let me pause for a second. So initially, the yield surface of this constitutive model is a cancellate. Originally, it looks like a bullet shape of cancellate. Modified cancellate was ellipse. This one is bullet shape, and let me animate it again. It has some over-consolidation ratio. It comes in, touches the yield surface. Because this is a loose sand, you see that generation of high excess pore water pressure to it, and it's going to go all the way towards liquefaction. It's coming, the level of shear that the material can endure is going to be very low. You can see that the static liquefaction. Like what I did for that more Coulomb material, let's go to this one. These are all the material properties that you have. You can manipulate them, you can change them and see which one is affecting the behavior in which way. So for this one, what I'm going to do, this initial state parameter is the one that is actually saying that the material is dense or loose. So when it's positive, it's usually indicating that the material is loose. So that's why probably I'm getting this liquefaction behavior. If this one was 0, so from what I had originally is going to be denser, you can see the behavior is actually changing. We don't see that liquefaction with the green material, the considered model that we have here. It is generating some excess pore water pressure, but because of the dilatancy tendency that we have for this denser material, it's generating the opposite negative pore water pressure, and because of that, your effective stress is increasing and the material can accept higher level of shear stress. If you make this one even more dense, let's say minus 0.01, you can see that, okay, the level of shear stress is going to shoot up. And with these tools that you have here, you can manipulate the properties as you wish and compare what you're calculating, what you're simulating to what you have from experiment. That way you can calibrate your material properties correctly. When you're happy with them, you can save the file, you can import the material properties from this file to RS2 and RS3 and carry out more successful simulation in those. Okay, let me go to question box. Reginald, if you want to add something to this.
No, so far so good, Alireza. No, you go ahead. Are there any questions?
Okay, I see a bunch of them here. Let me just maximize this window. Okay. That's my favorite question here. The first one that I see, Mahir is asking, can you add advanced consider model like PM4 sand, North sand, and all that? North sand is, I just showed it to you. PM4 sand, I have developed it, and I actually use RSData for my test and stuff. And the development is almost finished. It's going to be in RS2 and RSData and not RS3 because that's not a 3D model. That's pretty done. The only thing is that for advanced user or academia, if people want to develop their own models, which is what I actually did in my grad school, if I had a tool like this, that would help me a lot. At the time I was using Abacus and I was adding considered models to that one using the UMAC, and it was a pain to test it. So this one, we are giving you the option of user-defined material model. With this one, you can easily develop it, make that DLL, and test it way faster than attaching it to a finite element code. So this will be available soon as well. Okay. Do you have soil hardening model in RSData? The hardening soil model, if you would, you are referring to that one, yes, we have it, but it is not in the list of considered model that you can test it yet, but it's going to be there. Within the next patch of development that we have, all those considered models that we have in RS2 and RS3, they're going to be in RSData as well. Let me just open RS2 here so that I can show you what we have in there. So RS2 material models, and we have all these elastoplastic one. We have bunch of softening hardening one. North and SCR Barcelona Basic is here. This is our in-house softening hardening model. We have the Falias-Manzari bonding surface plasticity. PM4 sand will be added here. We have all those slide material model, lots of anisotropic material models, famous models from FLAC, famous models from Plaxis. So all of these, they will be in the next patch of development that will be included in our standard. Is it with the DSS test? So the library of tests that we have here, so far what we showed you, myself and Reginald, we showed you 3-axial test, but you have uniaxial test, biaxial test, simple shear test, general test, and like any kind of test that you would like. For example, general test, you are defining what is your initial state of stress and what kind of increment that you're applying to the system. It is going to be epsilon, strain, or anything. Any of these 6 components you can manipulate and apply that kind of test to the material. This probably is the one that you're asking for. You can use it, but otherwise, in many cases that I have to run like different fancy stress passes on my material to test it, I'll go to my general tab, and this list is also going to be extended because in many cases we need multi-stage tests, so those are going to be developed and added as well.
Somebody had asked Alireza about MI value. Okay. But the MI in Rocscience and RSData are exactly the same. If you set the same care fitting parameters, let's say you choose modified cuckoo, you choose basic, you choose absolute, whatever you choose, you get it's the exact same routines for care fitting. Correct, Alireza? We didn't change the care fitting routines.
In terms of material models, even the files are the same between these 3 programs. So RS3, RS2, and RSData, even the code is the same file. So everything is the same between them. Okay, any more question, Reginald, you see in there?
I was going to.
Yeah, for import and export to RSData, we are adding more functionalities to it because all these graphs that you see here, at the moment, you can right click on any of these and say copy data series and bring them to Excel. This option is there at the moment, but we are generating more robust, more user-friendly import and export from RSData. This is again, this is almost actually developed. Is if we could release it before Christmas, that would be nice, but probably it might go to the next year as well. Okay. Determination of elastic modulus for soil can be automatically performed by RSData. Yeah, if you have all these properties that you have in here, let me generate a new one. If you have your experiment, you can bring it into RSData. You can easily manipulate the properties that you have for a more cool material. Like, okay, I had the strengths and the stiffness. So the stiffness, you can change it as you wish and fit it to the properties that you have for the behavior that you have. The calibration that we have currently at RSData is only matching what we had in Rocscience, so it's only for strength of the material. But we will be developing a more general optimization algorithm to get you the properties and also all the parameters for the different consumer models that we have on RSData. So we can optimize the behavior and also the strength of the material and calibrate everything here, then take it to RS2 and RS3. The cyclic I answered, yeah, go ahead.
Oh no, there's one question on, can RSData compare the ROC test results with Hook-Brown failure criterion 2018? Yes, we do have the 2018 criteria. Correct, Alireza?
You're the man, yes.
Yes, we do. And like Alireza said, we'll still be doing some more work to make sure that we give you users more functionality to check your parameters. But yes, 2018 is implemented.
Okay, do you see anything else there in there?
I'm going through just to see whether there's anything else. User manual, we have the help file that comes with the program. That is
yeah. The help is there, but in many of tools that we had the comments as well that the help needs to be developed further. Yes, we are doing that, and we are in all the products that we have. The help is being improved like significantly. We have one of the highest priorities that we have at the moment is the help file and the documentation.
And then we also have a question on when will we add all of these models? It's the toughest question.
Yeah, so in terms of the code is there. The part of the code that has the consider model, as I mentioned, between RS2, RS3, and RSData, the code is the same, so the code are there. The only thing is that we have to give you this dialog, this one. So this dialog to be the same as the other ones that we have. In that case, then everything is going to be exactly the same between all these products. That was the original goal at the time that we started this project, but development is, this one is behind the other two, so it's going to catch up pretty soon. Okay. Do you have other soil hardening models? Yes, they are coming. All the stuff that I showed in RS2, they are all going to be there. All these models that we have for Plaxis, I think usually people refer to hardening soil as the one that Plaxis has. So this one is going to be there. These are all going to be there. And we have something, this hardening soil model, one of the softening hardening model that I actually have another example on this one tutorial that is shipped with the product. You can take a look at this one as well. Okay. Okay, if the spreadsheet is included with the software, yes. So this is our RSData. Let me go the spreadsheet that was for North End. If you go to recent tutorial folder, so that Nerlake Sand is here. Let me just copy paste this address and I open it in my browser. So this is that Nerlake Sand, this is that Excel file that I just opened for you. The Camp Clay ones, these are all those Excel files that I mentioned. These are all included with the software. These are all reference, these are public. This is actually we developed it in-house, and the other one from Mike Jeffrey, this is public also, and he sent the files to me, to myself, like between our correspondence that we have. Okay.
There was
Any further question? Yeah. Go ahead.
Yes, on how the cells are organized in Excel and how we can bring it into RS2. So for the rock side, for example, the triaxial, I mean, whichever way triaxial is, the format is sigma 3, sigma 1. So you put it in that, if you paste from that sequence, it's automatic. You don't have to do it just column by column. Most important thing is look in RSData, see how the columns are organized in Excel the same way, and it's straightforward. Copy and paste is what.
Correct. That is the current state, but in all our tools that we have, we are developing a unified import from Excel import, like a text file column structured data. So when that comes to our data as well, you can see, you can select which column is going to be which entity and all that. You can define each column and bring whatever column that you would like from that CVS file that you have. So that is also development.
Yeah.
Yes.
The data import wizard is what we're working on here.
Exactly. Now, so that is included a couple of tools that we have, but it's not all over the tools that we have. So that's going to be included as well. Okay. If you have any further questions, we'll be happy to answer them via email. So email us any question that you have, any concern, any feature that you are interested to see in there, we will consider for future developments. Please let us know. The feedback is very important to us. And Reginald, if you have anything to add.
No, not at this stage. So we'll make the stuff readily available to you. If you have more questions, and we're open to suggestions. We really know that we don't pretend we know exactly everything that you're facing and everything you want. So just let us know, and we'll do our very best to accommodate your suggestions. But as Alireza said, this is version 1 of RSData. There's a lot more work we are planning to do, especially on the calibration side, the soil side, calibrating other things, things other than just strength. That will also come. And there are more models to add. Alireza told you, everything we have in RS2 essentially will be in RSData. But thanks a lot for spending time with us. We appreciate it.
Absolutely. Thank you very much, everyone. So that will be concluding our webinar today. Hope to see you guys in future webinars that we will have. Bye for now.
Thank you. Bye-bye.